Hi, my name is Karen Meech, and I'm going to be talking about using small solar system bodies such as comets and asteroids to help us understand the formation of habitable worlds. Now, one of the main goals of astrobiology is to trace the physics and chemistry of terrestrial planet formation as it leads to the development of life. Now, this lecture is going to present some ideas of how we can use some of the small leftovers of the solar system formation to trace what may have happened within our solar system. So given that the goal is to trace the physics and chemistry of the terrestrial planet formation in the protoplanetary disk, we're not quite there yet observationally. Now, with facilities such as ALMA array in Chile shown here, we're starting to get a glimpse, but we don't yet have the sensitivity or the resolution to trace planet formation. If you take a look at the images here, these are some of the spectacular images that are now coming in from ALMA protoplanetary disks. But when you look at the scale, we start to get hints of dark lanes, which may represent where a giant planet is forming and is clearing out regions in the disk. But this isn't in the region of the habitable zone where we want to watch the formation of planets. However, the next generation of radio facilities and submillimeter arrays are predicted to have the capabilities that we need. Namely, they can image within the scales that are relevant to the habitable zone. They can also look at the chemistry of planet formation in the habitable zone. So today, with thousands of exoplanets known, potentially 10,000, and more than about 3,000 planetary systems, we may have potentially 50 habitable worlds. On the other hand, our solar system, so far at least, is unique in its architecture with the habitable planet in the habitable zone and the gas giants outwards. Now, water is one of the most abundant condensable molecules in space, so a solar composition gas should condense water-rich planets. We have some models on what may have happened in our solar system, but we're really lacking details. And of course, our solar system is the only one where we know that there is life. So this is an obvious system to understand how this process occurred and how we got materials into the inner solar system where we have a habitable and inhabited planet. So some of the big picture questions that we might want to address are, did the planetesimals come inwards from out in the outer solar system to form habitable planets? We get some ideas from meteorites. They give us clues, but it's not a complete picture. It turns out that what we really need to look at are the primitive small leftovers, the building blocks of the formation of our solar system, things that have never been heated and can give us clues as to what happened in our solar system. So what constitutes a habitable world? Well, we need to have liquid water. And this, if it's on the surface of the planet, means that the planet is constrained to be within a particular distance of its host star. And we'd also like to have organic compounds, a source of redox potential. Now, just having a rocky planet at just the right distance might not be sufficient if we don't have enough water. So one question is, how much water? If you have too little, obviously we don't have enough for liquid oceans and development of life. But on the other hand, if you have too much water, that's not good either. If you have a water world, and in fact, if our world had as much as 5 ocean volumes of water, this would cover the continents, and that would inhibit weathering and the liberation of some of the chemicals that are necessary for life into the environment. Also, if you have way too much water, such as 50 oceans on our planet, the pressure at the base of the ocean will be so high that you will get high pressure forms of ice forming, and that will completely shut off the normal carbon silicate weathering cycle on Earth. And that's one of the things that controls our climate and helps keep the world habitable. And in fact, if you look at the inner solar system, in our solar system, we're actually quite dry. Mercury is very dry. Venus and Earth, while similar in size, certainly don't have the same amount of water, and Venus probably lost what it got as it had a runaway greenhouse effect. Even the Earth, which we think of as a water-rich world, doesn't have very much by mass. Estimates range from about 0.05 to 0.1% by mass. The moon is dry and Mars is quite dry. So let's take a look at some of the types of solar system bodies that could be used as tracers of the history of delivering materials to Earth to make it habitable. And these small bodies are important because they're likely never have been heated or not enough to lose their volatile materials or their chemical fingerprints, not enough to erase the history that they can tell us about the early solar system. So looking at the various classes of primitive tracers, we have meteorites. These have been extremely well studied in the laboratory, although most people don't realize that we really have good samples from about, in terms of the primitive bodies, about 15 parent asteroids. And what we see in these primitive bodies is that they all contain some level of water and they've been altered. So there's been water-rock interaction. So they aren't exactly pristine. We have icy asteroids. These are bodies that are within the asteroid belt, but which apparently exhibit cometary activity and may preserve the early solar system history. These have not yet been explored. We have comets, which are the icy bodies that formed farther out in the solar system and exist today all over the solar system. We've observed many of these, both from the ground and with missions, but we haven't observed all types of comets. We have the icy small satellites around the gas giant planets. Some of these are really intriguing from the perspective of liquid oceans under the surface and the potential for astrobiology. These are not quite as good as comets because they're bigger and they've certainly been heated, which erases the signature. And then finally, a new class of small bodies, the interstellar objects, are almost completely unexplored. So let's take a look first at what we know about the most common primitive bodies that we've been studying for several decades now. Let's look at what we've learned from comets, both from ground-based observations and from space missions. So the very first, ideally we'd like to look at the chemistry because this gives a tracer of what was going on in the protoplanetary disk. And the early chemical measurements of comets were done spectroscopically at optical wavelengths. And what you get at optical wavelengths are not the initial composition of the object, but you get what's called daughter species. It's fragments of the more complex compounds that are on the cometary surface. But this was the easiest observation to make. So a couple of decades of observations by several groups. The first paper that came out on this was by Mike Ahern. He was looking at the ratio of carbon chain compounds, C2 and C3, to other species such as CN. And what he found was there was a range of common values. However, some comets were found to be depleted in these carbon chain species. And the idea was that there's probably some sort of thermal process which relates to where the comet formed that has caused a depletion in these chemicals. At first, it was thought only to be short period comets, but it's not exclusively short period comets. Even long period comets are seeing this depletion, although not as great an extent. The short period comets likely formed in the outermost solar system in the vicinity of the Kuiper belt and are now migrating inwards. The long period comets, on the other hand, likely formed closer to the sun, near the giant planets, and then were kicked out subsequently to this vast reservoir called the Oort cloud. So one would expect a different chemistry, all things being equal, because they formed at different distances from the heat source. Now, with more technology as time went on, astronomers started to observe the chemistry of comets in the near infrared with high resolution spectroscopy. And this allowed us to detect the parent species or the actual compounds that are on the comet before they photodissociate once they leave the nucleus. And this is some work after a figure by Mike Muma and Steve Charnley. And what they found was a range of chemical compositions. Some comets were enhanced. They had an abundance of these organic species. Others were more or less average, and some comets were depleted in the organic compounds. And again, just like the work with Micah Hearn, it was not shown that these were correlated with where we thought they formed. Everything was mixed up. On the other hand, some species were correlated with formation distance. In particular, some comets were very rich with carbon monoxide. Most comets are primarily water ice in abundance, with some CO2 and some CO, and then a whole bunch of minor species. It was only the long period comets that were abundant with CO. Isotopic measurements have been made with very high resolution spectroscopy. And these are also interesting. The D to H, the deuterium to hydrogen ratio, is elevated with respect to the Earth. The nitrogen isotopic ratio is about 2 times elevated compared to Earth, whereas the carbon isotopic ratio is about the same as the Earth. And again, no apparent difference between where we think they formed. So what about the space missions prior to Rosetta? One of the very interesting things, it had always been believed that comets were driven by water ice sublimation. Namely, comets are a mixture of ices and dust. And as sunlight heats up the ice, primarily water ice, it will convert to a gas. And in the low gravity of the comet, this will push dust away from the surface, creating the visible tail, which is seen as sunlight reflected off of the dust. However, once we got up close to comets, we saw that it's not just water that's controlling the activity. Carbon dioxide also was a very important player, but because this is a more volatile ice, it sublimates at a much lower temperature. It was predominantly subsurface, and therefore it would take a long time for the heat to get down to these ices. And so you could get activity even during the nighttime as the heat gets down to deeper layers. We learned, and we'd known this a bit from ground-based studies, but from the missions we found that comets are very low density and they're very good thermal insulators, which is exciting because it means just below the surface, there's the potential to preserve the primordial signature that we're looking after. Surfaces are very dark, covered in organic rich compounds, but we'd seen that from some of the work from the ground. In terms of the dust material, the silicates showed a very complex history. They'd been processed, sometimes at very high temperatures. The Stardust mission, for example, showed some of the dust that was found in Comet Field 2 actually had seen very high temperatures. So this gave us a first clue that there was a lot of mixing going on in the solar nebula. I'm not going to talk too much about meteorites, but for completeness here, I just wanted to mention again, of all the different primitive classes, we see that there was a lot of water, a lot of interaction between the water and rock, but none of the materials chemically or isotopically matched Earth. So we don't have samples of the young Earth. Now taking a look at the results after the Rosetta mission. This was a mission that launched, a European mission that launched in 2004 and reached its target, Comet 67P, in August of 2014. And then it stayed with the comet for 17 months, orbiting down as close as 10 to 30 kilometers from the surface. And we got spectacular images of the comet, really getting a close-up look as the comet got closer to the sun. You can watch the evolution of the activity. Now, some of the things that were learned were confirming what had been learned from 20 to 30 years of ground-based observations, but there was a lot of new and exciting science. Abundant super volatile material. We'd never seen molecular oxygen. We'd never detected nitrogen. We'd never been able to detect noble gases. A rich array of organic compounds. So if comets did indeed deliver material to the early Earth, they would have delivered a lot of organics. And we see a lot of signatures from the protosolar cloud prior to solar system formation. We're left with a lot of big questions because a lot of the science really looked at details of how the comets work. But we still, after the mission, don't know exactly where comets form. It's probably a range of distances in the solar system. And we didn't answer the big question of what role do they play in forming a habitable world. So really what we're trying to do is to use the small leftovers of the process of building planets from the earliest stages of the collapse of a cold, dark cloud of gas and dust through the development of a protoplanetary disk, which will have something called the snow line, inside of which the warmth from the young protostar is enough to keep the gases in a gas form. Outside of this, things are so cold that things freeze into ices. We want to look at the stages. The comets represent the stages where we have planetesimals, building blocks, prior to getting incorporated into the planets. And then these were tossed outwards into the outermost disk where they're preserved today. And we're hoping to use these to understand some of these steps. Well, what it's going to take is an understanding of not only what was going on physically, but we're also going to need to take a look at the chemistry during the era of building planets. Now, this is a really nice figure borrowed from Ilse Cleves, which illustrates schematically what's going on in the young protoplanetary disk. If we're looking at the gas, we see that we've got a flared disk. It collapses first in the center. We've got the young protostar starting to heat the disk. You'll have a gap between the star and the inner edge of the disk. The surface material on the disk gets heated from the young star from radiation from space. And so you tend to get an ionized hot surface. You get a warm layer as we go down into the disk, and this is where molecules can start to form. This is a rich region for chemical reactions. And then at the midplane, it's very cold, and you can get freeze out in the midplane onto the icy grains. Now, there's going to be a gradient in temperature both vertically as well as horizontally. It'll be warmer towards the young protostar. At the same time, there's going to be a lot of motion in the disk. You're going to get turbulence in the disk. We're going to expect that there will be mixing both vertically and radially. And then as the ices condense out onto the dust grains and the dust grains start to coagulate and grow larger and larger, there will be movement in the disk with the dust grains. So any type of model that is trying to understand what's happening during the planet building process becomes very complicated and has to take into account a lot of factors. So what are we going to use to trace this process? One of the powerful tools for tracing what was going on in this period chemically is to use isotopes, because they're very sensitive to the physical conditions within the disk, the temperature, pressure, ionization states. So one of the earliest ideas to trace the early solar system materials was to look at the deuterium to hydrogen ratio. This is initially set during the Big Bang explosion, but then in cold molecular clouds, we get extreme enhancement of the deuterium because a lot of the reactions that form molecules, ion molecule reactions, tend to favor the formation of deuterated species. It's a lower energy process. So the idea was that we probably would inherit material from the interstellar medium that has a much higher D to H value than you would expect from the Big Bang. And then during disk chemical processes, this can get lowered as the materials are heated up. Now, it had long been known that the Earth's oceans had a very high D to H compared to what we expected in the protosolar nebula. It was about a factor of 6.5 times higher. With the first space mission to a comet, the Giotto mission, which carried a mass spectrometer, it showed that the D to H was elevated in comet Halley by about a factor of 2 over that of the Earth's ocean. So this gave people the idea this could be the source of Earth's ocean water. And a lot of people spent a lot of time trying to look at D to H in comets after this. So looking a little bit at the history of this, this is a schematic diagram that shows D to H ratios in the solar system. Here's the measurement from missions and gas giants, the expected protosolar nebula and the interstellar medium measurements. Meteorites, we've got the Earth ocean here. Meteorites best match Earth's ocean, but it's not just D to H. A lot of their other compounds don't match precisely what we have on Earth. So the very first measurement from Halley was high. And then as ground-based telescopes started to get more and more measurements, all of the comets seemed to be high. And this was starting to create a problem because they're too high. They don't match Earth's oceans. But the very first D to H measurements were all done on long period comets, which are brighter. So everyone was eagerly awaiting the first measurement in a short period comet. And this was done for the epoxy mission target, 103P Hartley 2. And it turned out it was close to Earth ocean water value. Now, this was a problem because all of the theories predicted, since Jupiter family or short period comets form farther from the sun where it's colder, people expected the D to H to be higher. So people that did the disk chemical models scrambled to find new mechanisms and new models that would cause a lower D to H in the outer solar system. Then the Rosetta mission comes along, and the measurement of this short period comet was one of the highest in D to H. So people threw up their hands and said, we don't know where, this isn't giving us a good signal, and comets didn't bring in Earth ocean water. Well, certainly these did not, because they still exist. So what's going on? Well, if we take a detailed look at one of the disk chemistry models, for example, this one from Karen Willesee in 2009, it's just representative of what these chemical models look like. They're very complex, and what's shown here is a function of distance from the protostar and height above the midplane is the relative abundance of this particular chemical species in the disk. So you can see it's not a smooth function of either distance from the star or height above the midplane. Now, if you were to take a trace through this, this would give you the abundance predicted for this species as a function of distance. So here we show a similar graph. It's just distance versus D to H. Here's the Rosetta measurement from comet 67P. This curve represents the initial expectation of D to H getting higher in the outer solar system from disk chemistry models. This is the one that said, oh, it better come down farther out in the outer solar system to match what we saw with short period comets. And here's a trace from one of Karen Willesee's models that shows the complexity you might expect along the midplane. The different colored regions show regions in the disk from where material could have scattered from the outer solar system and reached Earth based on different models. What you can see is this one measurement is consistent with two chemistry models, and that's consistent with most of the dynamical models. So in other words, you really have to take account of both the chemistry and the movement of material in the young solar system, which will rearrange the signal. You'll get the fingerprint imprinted as the material freezes out in the midplane, but then it gets scrambled up. So a single isotope won't tell us the story of what happened. So now let's take a look, a small deviation into, we're trying to compare this when we're trying to understand the formation of habitable worlds, namely Earth. We're comparing the signatures that we see chemically with Earth oceans. Is that really the thing we should be comparing it to? So one initial question is, how much water does Earth have? Everyone knows that 71% of the surface is covered by water. But if you take a deep look at how much water scientists think there might be on Earth, there's a wide range of opinions. Everybody can count up the amount of water in the ocean and atmosphere, there's good agreement. But as you go deeper and deeper into the Earth, it becomes part measurement, part theory, as well as lab experiments. For example, how much water could the rocks in the mantle hold based on the temperature and pressure conditions? And you can test that in the laboratory. So in the end, you can see that the total amount of water on Earth varies greatly between different estimates. Most scientists think conservatively we may have somewhere between 3 and 5 oceans worth of water on the Earth. So this begs the question, if there's more water inside the Earth than on the surface, maybe the D to H comparison that we're making is not the right one. We should not be comparing it to ocean water. It should be inside the Earth. And very interestingly, I was at a meeting in Iceland in 2004, and just as a side event after the meeting, there were some field trips planned. We ended up going to a geothermal site where there was gas coming out of the ground. And one of the geologists said, oh, it's okay, it's steam, it's just water, and it's relatively cool. You can go over and approach it. But then she said something that got me thinking. She said, it's primordial water coming from deep inside the Earth. That got me all excited. I thought, finally, we can measure something that's not ocean water, because that had always bothered me, because surely there have been chemical processes that have altered the D to H in the oceans. So I talked to some folks in Iceland, and they said, well, in fact, she's wrong. This is not primordial. It's rainwater that gets down and gets heated up volcanically and comes out again. However, there are sources of primordial water that can be accessed. And these come from deep mantle plumes, material that's coming up from near the core mantle boundary. And many of these materials can survive transport. They're locked in very high temperature minerals, such as olivines, pyroxenes, diamonds. And the key is, there is a signature that they are preserving material from space. And this key is the helium isotopes. This ratio, again, was set in the early universe. And what we find on Earth is typically this ratio is very small, because on Earth, radioactive decay is constantly making helium-4. However, there are certain regions on Earth that have an extremely high helium-3-4 ratio. That's a signature that material has not mixed with radioactive decay products. And so I got excited and I said, has nobody ever measured D to H in these rocks? And they hadn't, because the technology wasn't here yet. So there's various regions on Earth, such as Iceland, Hawaii, other places, where we do have the ability to look at the D to H inside the Earth. So our astrobiology group in Hawaii started to get some samples. It was interesting for me because I'm trained as an observational astronomer. So to actually get a rock hammer in my hand and look at the rocks was a lot of fun. You take the rocks back to the laboratory, look at them in an ion microprobe. And one of the postdocs in our group, Lydia Hallis at the time, she did all of the measurements. And what she found was that the D to H in the samples that we had from both Greenland and Iceland showed that the D to H of the water inside the Earth was lower. So in fact, if you're going to do this experiment, you've got to measure the right comparison sample. So getting back to our isotopic fingerprints, isotopes will trace different physical processes and give us unique data about the early solar system. We've talked about D to H, but that's not the only one that we could look at. Another one that cosmochemists, or the people studying the meteorites, look at are the oxygen isotopes. Now, this is a diagram from the meteorite community looking at the ratio of the 1617 and 1816 oxygen isotopes. Oxygen has 3 isotopes. And there's a wide range of values in the solar system. And it was in an attempt to explain the cause of this variation in the solar system materials that the cosmochemists came up with the idea of oxygen self-shielding. And the idea is that there's a lot of carbon monoxide in the protoplanetary disk, and this can get photodissociated at ultraviolet wavelengths. And the different isotopologues, the CO16, CO17, and CO18, will get photodissociated at slightly different wavelengths. Once it's broken apart, the oxygen will combine with hydrogen and eventually make water. Now, the most abundant isotopologue, oxygen 16, will eventually use up all of the ultraviolet light at that wavelength. And so we will stop breaking apart CO for the O16. So we will only be producing, as you go deeper and deeper into the nebula, the oxygen 17 and 18. So you'll be manufacturing heavy water. And it was believed this was one mechanism for creating this isotopic fractionation in the solar system. The process here is a different physical process from the ion molecule reactions, which fractionate or enhance the deuterium abundance. So it should have a different heliocentric distance or temperature dependence. Nitrogen also can fractionate. There can also be ion molecule reactions like D to H. There could be self-shielding, but because it's a different molecule, it will have a different pattern in the solar system. Noble gases can also give us a clue to where things form. They can get trapped as water condenses at very low temperatures, and the relative abundance of the different isotopes of the noble gases can give an idea of the temperature. So by looking at multiple chemical species isotopically, we can get some hints as to what was going on in the early solar system. But that's just getting at the chemical fingerprints. We still haven't talked about this dynamical scrambling up of the planetesimals. So for that, there was an interesting discovery in 2018 with the Pan-STARRS telescope in Hawaii. Richard Wainscoat came into my office. He's leading the Pan-STARRS survey for near-Earth objects. And he said, Karen, we've found an interesting long-period comet. It's on a long-period comet orbit, but it does not look very active, and it's near perihelion. So it looked like this, just a tiny tail, very low activity. Normally, long-period comets at this distance from the sun have enormous tails. So I got excited. I said, yes, this is very interesting. Now, while we were trying to get follow-up observations and reduce the data, a second one was discovered, and it was actually analyzed first. And its spectrum was very unusual. Every comet that we've ever looked at the surface is organic rich and red, namely the spectral reflectivity increases more or less linearly as you go to longer wavelengths. So here's the spectral reflectivity of this second object. The colloquial name we're giving it is Manx, for the nearly tailless cat, since these things are near the sun, but are nearly tailless. So this Manx had a spectrum that started to linearly increase and then had a dip near 1 micron. And this is typical of inner solar system rocky S-type asteroidal material, which cannot form in the presence of water. Yet this thing had a tail, and it was behaving as if water was sublimating from the surface. So we think this may be material that formed near the snow line in the inner solar system. This little cartoon here is showing something that formed in the inner solar system, got ejected by a close approach to a giant planet into the outer solar system, and over a long period of time, eventually makes its way into the Oort cloud, this reservoir where the long period comets are stored. And just like the long period comets today, when a nearby star gives them a gravitational push, made its way into the inner solar system. Now, what's exciting about this is discovering the fraction of these that may be coming from the Oort cloud that have this inner solar system signature can help us distinguish between different dynamical models. And I'm sure you've already heard at this conference a lot of detail about dynamical models, but let me just remind you of how these observations are going to be useful. So if we take a look at this nice cartoon by Francis de Mayo, it represents two dynamical models. Up at the top, it's representing the Grand Tack model, where the gas giants are starting to grow in a planetesimal disk while there's still gas around. The blue planetesimals represent icy planetesimals in the outer solar system. The red ones represent rocky planetesimals. As the gas giants grow and migrate in the disk inwards, they can drag icy material inwards, they can kick rocky material outwards. Eventually, they slow down and migrate back outwards. The gas disk dissipates, and then the giant planets can interact with the remainder of the disk. And this was actually the Nice model, scattering things until we have the distribution of material we see today. Other models, such as the one by Raymond and Isidoro, which is not intending to predict any particular architecture, but to describe a process, suggest that you will have massive scattering of planetesimals, whether or not the giant planets move. Now, obviously, if the giant planets migrate inwards, they're going to more effectively scatter the rocky material outwards. So the amount of rocky material relative to icy material in the Oort cloud may give us a clue of which type of process was operating. So in order to do that, we've undertaken in Hawaii a big observing program of these Manx comets. The intent is to get about 100 of them. They're discovered with pan-stars, quite faint, and so we initially follow them up with Canada, France, Hawaii telescope to get a good orbit, get the initial brightness estimate, and then follow up with Gemini to see what their surface is like. And so far, this is forming the thesis of my PhD student. So far, we're seeing a wide range of surface colors, much broader than what we see with comets. So we're seeing a big mixture of material that's coming in from the outer solar system. So this is one way in which these small bodies can give us a clue about the dynamics. But another clue has recently come from the cosmochemical community, namely some meteorite studies. In 2017, a paper came out in PNAS that was looking at isotopic studies in chondrites, non-carbonaceous and carbonaceous chondrites. And what the team found was a very distinct chemical signature when they looked at the molybdenum and tungsten isotopic ratios for these two types of chondrites. And you can see that the ratios are very distinct between the two. Their interpretation of this, since the ages, they were concurrent in age, was that for millions of years, maybe from 1 to 4 million years, these two reservoirs coexisted, but they had to be kept physically distinct. And so they hypothesized that the best way to do that was if Jupiter formed very early, by about 1 million years, and grew large enough to open up a gap in the disk, then material that would be naturally, small material naturally flowing in from the outer solar system under the influence of Poynting-Robertson drag would feel a pressure bump here and get stopped. So you would stop having a flow of icy material into the inner solar system. So some of the chondrites form outside the gap and some form inside the gap, and perhaps our Manxes formed near the boundary of the water ice line. So looking at this in terms of the ALMA schematic, where we see in other planetary systems, we see these disks that have opened up. Suppose Jupiter forms early, opens up a gap. It impedes the flow of icy material inwards, but Earth forms in the inner disk where it's warm and presumably dry. As the giant planets grow, whether or not they migrate, they're going to scatter planetesimals. They will scatter them outwards and inwards. Anything that gets scattered inwards will make it to Earth, will hit the Earth, but it will also get implanted in the asteroid belt where we can still observe it today. From where it scatters this material depends on when Jupiter formed, and where it opened a gap. So either Earth captured volatiles from just the gases in the inner disk, or it was delivered from scattered planetesimals that may still exist in the outer asteroid belt. So the idea is this would be the key place to look for signatures of what happened in our solar system. We need some ices in the asteroid belt that record this history of volatile migration. We'd like them to be close enough that we can actually do detailed chemical analysis. And it has to be a small body so that the signature has not been altered. And as we've seen from the isotope ideas, we have to have multiple chemical markers to measure so we can detangle the story. So what evidence do we have for ices in the asteroid belt? Well, certainly from the Dawn mission, we've seen spectacular evidence of ice on Ceres, as well as Vesta. Unfortunately, both these bodies are so large, they have almost certainly been thermally processed. So these are not good places to look for ices. There's some other relatively large asteroids that also have evidence of ice. But again, we need to get back to the small body because we don't want things thermally processed. Well, the Pan-STARRS and other surveys are constantly finding new evidence of comet-like tails in the asteroid belt. And here's one that was fairly recently discovered in 2019. This looks cometary. This is a Hubble Space Telescope image of the asteroid 6478 Gault. So it looks like a comet tail. But when you look at it in more detail, and this graph here shows its light curve as a function of true anomaly, which is position along the orbit. So true anomaly of 0 is at perihelion when it's warmest. True anomaly of plus or minus 180 is at aphelion. So you can see here in 2016, oh, by the way, this dark curve represents the brightness of the nucleus as it gets closer and farther from the sun and Earth. Here in 2016, you can see it was much brighter than it was predicted, and it also had a tail then. So that would be consistent with a thermal process. However, the one that I just showed you in the HST image here from 2019, this one was nowhere near perihelion. And there was also a little bit of activity here, also nowhere near perihelion. So apparently whatever's happening to Gault is not thermally driven. And in fact, many teams think that this may be an asteroid that is spinning so fast, it's ejecting material. And this is also causing its color to change rather dramatically as a function of time. We've seen evidence of other things in the asteroid belt that's not sublimation driven, but may be due to some thermal process, the fracturing of surface materials getting ejected into space. On the other hand, we do find things in the asteroid belt that are small bodies that we do believe have ices in them. And these are the things that are being called main belt comets. And the characteristic of these is that they have repeated activity that rises at perihelion and fades afterwards. And there's been about 13 of them now that have recurrent activity 2, 3, 4 perihelion passages. And the only thing that can cause this is a thermally driven process, namely sublimation of ice. And this diagram here just shows where they are in terms of orbital space, function of semi-major axis and eccentricity. All of the squares represent bodies that have been seen with tails, and the blue ones represent the objects that we believe are driven by outgassing. Now, all of these have small, flat, featureless spectra that look more like comets. Some comets have flatter, shallower slopes. In spite of seeing tails in these, nobody has ever detected gases. However, at the distances they are at from the sun and the amount of dust that we see around them, the amount of gas that you would need to lift the dust is so small that it's below the detection thresholds for even the largest telescopes on Earth. So given that we want to do isotopic measurements, which would require high resolution spectroscopy from Earth, If we can't even detect the gas at all, we cannot do this experiment from the ground. Now, many of these are often associated with asteroids that have collided and broken apart, so a collisional family. And the concern might be that these aren't primitive because they came from a bigger body. But even when bigger bodies differentiate and heat, you will get the surface materials that will be unaltered. And so we actually think the main belt comets in the collisional families come from these. So the idea would be to send a spacecraft to actually make isotopic measurements of several species, deuterium to hydrogen, oxygen, nitrogen, noble gases. And just as we saw with Rosetta, we can compare dynamical models and chemical models. And maybe one isotopic measurement doesn't solve the question. A second isotopic measurement, which would depend on different physical processes, may have a different solution that is not unique, but it may overlap with some of the solution from the deuterium to hydrogen. As you add more and more chemical markers, you may end up with a single solution that works for all of them, which would tell us that we understand where things came from. Or it may be that there's no solution and we need more models. So many of us, European colleagues and those from the US and Japan, are working to get a mission pulled together that we're calling Proteus, with the intent of exploring the main belt comets to try and understand how habitable worlds form. So the idea would be to launch the spacecraft with solar electric propulsion, have a slow trajectory, making it out to the asteroid belt, where we would fly by and a few objects, but then rendezvous with two main belt comets, ideally 238P Reed and a binary system, 288P. In addition, of course, you would do both not only the isotopic science, but characterize these new bodies in terms of their surface features, their color, look for evidence of hydration, and understand the sources of activity. So we're working hard to try and get this funded. Well, for the last part, I want to talk a little bit about where we go from here in understanding some other small bodies with missions. Now, to date, all of the missions that have explored in detail these small bodies have gone to the Jupiter family comets. So if you imagine the heritage coming from the very start of solar system formation down to the protoplanetary disk, the short period comets originated in the Kuiper belt. They get scattered inwards, spend a significant amount of time in the Centaur stage as they evolve dynamically into the inner solar system, where they end up being Jupiter family comets, where they spend a long time in the inner solar system getting heated. We've only had one comet that's came from a different region, formed in a different region, and perhaps is not as heated, and that was with the Giotto mission, which went to a Halley-type comet. These come from the Oort cloud originally, become long period comets. And in this case, this has a relatively short orbit that's less than 200 years. What we have never visited are things that are even fresher, things coming more directly for the first time from the Oort cloud, long period comets and Manxes, which may sample the inner solar system material. I've already talked about the main belt comets. And then of course, this new class, which are the interstellar objects, which may allow us to do the same experiment, but holding a piece of material not from our solar system, but the leftovers from the birth of another solar system. So to just give you a quick glimpse at this, because I know you're hearing other talks on interstellar objects, we've only had two objects discovered so far. One Eye was found to be very small, no apparent activity, although because its orbit changed due to non-gravitational motion, it must have been outgassing. An apparent very elongated shape that's a little bit hard to explain. Then we have 2I that looks more like a typical comet with a tail, but the chemistry was a little different, very enriched in CO, more so than anything else in the solar system, but it was also carbon chain depleted. So in terms of these two objects, one looks like a typical comet, one doesn't. Both of these have generated a couple hundred papers and growing. The intense interest in these things, especially for 1I from the peculiar shape, has led to a really rich interpretation of the formation of planetesimals in young solar systems, their ejection into space, and travel to Earth. So clearly, these things are going to be of interest for space missions. But there's some challenges. And let's look at one of the first ones. Right now, these would be very hard to reach because from the time at which they're discovered until the time they're too faint to observe from Earth and potentially too far to get to with a spacecraft is very short. So let's take a look at our first interstellar visitor, 1I. It was discovered on October 19th, 2017. And then by the 22nd, we knew it was hyperbolic, and everybody started to put in proposals and get their proposals for telescope time approved. And we had about a week where it was bright enough to observe. So this is when the observations started. And you can see within a week, it had faded significantly. And at these brightnesses, it's getting very hard to do a lot of the science you would like to do to characterize the object. There were some lingering observations out for 2 months, but at this point it was too faint for any facilities. Our second interstellar object, Borisov, was much better. It was discovered prior to perihelion. It wasn't coming as close to the sun. 1I came inside the orbit of Mercury. Borisov only came to 2 AU, which meant it's not moving as fast at perihelion. And so it was also better placed for observing. So it's had a continuous observing campaign from about August 2019 through September of 2020. And it's coming out of solar conjunction this month and will be observed again by HST. However, there's also other issues with looking at interstellar objects from a mission. So clearly interstellar objects, long period comets, and Manxes could give us some transformative science because these bodies have never been heated. So they can give us both insight into our solar system and others, but there are some challenges. First of all, how many are going to be discovered with enough lead time? As you saw for the 2 ISOs, we don't usually have much lead time. Here's a diagram that shows the discovery dates and the distance from the sun at which these comets were discovered. And you can see in the distant past, it looks like they're discovered far from the sun, but it doesn't take very long to come in on these orbits to the inner solar system. Once the big surveys started to come online, you can see a huge increase in the discovery. Moreover, we're seeing discoveries much farther from the sun, and these blue dots represent the Manxes. So we're thinking that when LSST, the Rubin telescope, gets on the sky, we may be able to get as much as 1 interstellar object per year, and we will routinely be detecting the long period comets or long period objects, Manxes and comets, maybe 10 years prior to perihelion. This gives us a chance to mount a mission. Another issue is these long period comets are more likely to be very rich in CO. As we saw from the epoxy mission, subsurface outgassing from CO2 can knock large chunks of material off the surface. These dots here are not stars, they're chunks, centimeters in scale, up to tens of centimeters. So to have this debris field makes the encounters much more dangerous. Also, unlike Jupiter family comets that we've visited to date, long period objects can have any orbital inclination, which makes mission access difficult. So here's the challenge. If you want to do some of this high-level science, the isotopic work, you want a rendezvous where you spend time at the object. That's simply not possible with these objects on long period comet orbits. As we look up here, this is the launch energy versus the encounter speed. Giotto was destabilized by a 1 gram grain impact at nearly 70 kilometers per second. So you'd like really low encounter speeds. And as we can look at the scale here, this is the fraction of objects that launch within half a year from perihelion and have a relatively short time of flight, less than 10 years. And you can see with low encounter velocities, none of them. On the other hand, if you're willing to take really high encounter speeds, you can start to get a larger fraction. So with high launch energy and, which is expensive, high encounter velocity, we can reach most of the objects we might hope to discover. If you have lower launch energy, but you're willing to take the high encounter velocity, we can still get to a good number. On the other hand, if you have high launch energy, you're willing to spend the money, but you want low velocity, very few of them, unless you have a special case. And this was one example of comet C2017 K2 pan-stars that was discovered about 10 years prior to perihelion. And there was a trajectory that could take advantage of a Jupiter flyby to give you a low encounter velocity, less than 2 kilometers per second. But that's still not a rendezvous, which is what you'd really want if you want to do some isotopic work. So what are some of the thoughts? Certainly compelling science, but we need a different way of doing missions. We can't have the standard paradigm where it's about 6 years from proposing a mission until you launch, because the current paradigm requires that we know the target. We need to have a rapid response, and you need to be able to propose for targets that have not yet been discovered. Plus, you want to maximize the science for these things to enable looking at some of these big picture questions about how solar systems form. So one idea is to have a multi-spacecraft architecture where you have a mother spacecraft and then a lot of smaller spacecraft that arrive with the mother craft, such as CubeSats, such that these can take the risk of going in close and doing some of the experiments. So you effectively get a rendezvous-like mission, but with a flyby scenario. JPL actually did a study for this comet C2017 K2 and found that you could send 2 small satellites together for a flyby and accomplish some science with our technology today, but there was no path for a rapid response such as this, no way to get the funding. At a Keck Institute science workshop a couple of years ago, a team got together to see what the sort of mission timeline might look like. You could have a mother spacecraft with a whole bunch of subcomponents on it that releases everything in advance, and a scout could come do some initial reconnaissance, look at the materials in the near nucleus environment. You could have impactors that could help release some gas and dust, where you could fly laboratory small satellites through a plume to collect samples, everything relaying it back to the mothership, which stays off at a safe distance. So these will be the wave of the future for the new innovations in terms of space missions. But I think if we want to go after these high value targets, such as long period comets, Manx's, interstellar object, we're going to need a new way of doing missions. So to summarize, I think these small leftovers in our solar system are certainly going to be the keys to telling us how we got the necessary ingredients for habitability, at least water. And if water comes in, you're bringing the organics. In our solar system, we've got various types of bodies that we can use to detangle this, both the Manx comets, long period comets, and the main belt comets. But we do need to have good isotopic measurements in the asteroid belt. And I think the way to do that is with a mission such as Proteus, but we're also going to need reactive missions if we want to go to these more exciting long period targets. Thank you very much.